Section 11.6, Testing Spring Security and OpenID Connect. The importance of writing auto tests is usually apparent to developers. Still, things can get challenging when it comes to security, and it sometimes ends up not being covered by automated tests because of its complexity. Fortunately, Spring Security provides several utilities to help you include security in your slice and integration tests in a simple way. In this section, you'll learn how to use the web test client support for Spring Security to test OIDC authentication and CSRF protection. Let's get started. Section 11.6.1, Testing OIDC Authentication. In Chapter 8, we tested REST controllers exposed by Spring WebFlux by relying on the @Spring WebFlux annotation and web test client. In this chapter, we added a new controller, user controller. So let's write some auto tests for it with different security setups. First of all, open your Edge Service project, create a user controller test class annotated with WebFluxTest, usercontroller.class, in src/test/java, and autowire a web test client bean. So far, the setup is similar to what we used in Chapter 8, a slice test for the web layer. But we need some extra setup to cover security scenarios, as shown in the following listing.
Listing 11.17, Defining a class to test the security policies for user controller.
Since we configured Edge Service to return an HTTP 401 response when a request is unauthenticated, let's verify that happens when calling the /user endpoint without authenticating first.
See this code?
To test the scenario where a user is authenticated, we can use mock OIDC login, a configuration object supplied by security mock server configurers to mock an OIDC login, synthesize an ID token, and mutate the request context in web test client accordingly. The /user endpoint reads claims from the ID token through the OIDC user object, so we need to build an ID token with username, first name, and last name. The roles are hard-coded in the controller for now. The following code shows how to do that.
See this code?
Finally, run the tests as follows.
See this code?
The testing utilities supplied by Spring Security cover a wide array of scenarios and integrate well with Web Test Client. In the next section, you'll see how to test CSRF protection using a similar approach. Section 11.6.2, Testing CSRF. In Spring Security, CSRF protection applies to all mutating HTTP requests by default, such as post, put, and delete. As you saw in previous sections, Edge Service accepts post requests to the /logout endpoint to initiate the logout flow, and such requests require a valid CSRF token to be executed. Furthermore, we configured the RP-initiated logout feature from OIDC, so a post request to /logout will actually result in an HTTP 302 response, redirecting the browser to Keycloak to also log the user out of there. Create a new security config test class and use the same strategy you learned in the previous section to set up a Spring WebFlux test with security support, as shown in the following listing.
Listing 11.18, Defining a class for testing the authentication flow.
Then add a test case to check whether the application returns an HTTP 302 response after sending an HTTP post request to the /logout with the correct OIDC login and CSRF context.
See this code?
Finally, run the tests as follows.
See this code.
As always, you can find more test examples in the source code repository accompanying this book. When it comes to security, unit and integration tests are critical for ensuring the correctness of an application, but they are not enough. Those tests cover the default security configuration, which might be different in production. That's why we also need security-oriented auto tests in the acceptance stage of the deployment pipeline, as explained in Chapter 3, to test applications deployed in a production-like environment. Polar Labs. Until now, the only application supposed to be accessed by users directly was Edge Service. All the other Spring Boot applications interact with each other from within the environment where they are deployed. Service-to-service interactions within the same Docker network or Kubernetes cluster can be configured using the container name or the service name respectively. For example, Edge Service forwards requests to Polar UI via the polar-UI:9004 URL on Docker, container name : container port, and via the Polar UI URL on Kubernetes, service name. Keycloak is different because it's involved in service-to-service interactions. For now, those are just interactions with Edge service, and also interactions with end users via the web browser. In production, Keycloak will be accessible via a public URL that both applications and users will use, so there will be no problem. How about in local environments? Since we don't deal with public URLs when working locally, we need to configure things differently. On Docker, we can solve the problem by using the host.docker.internal special URL configured automatically when installing the software. It resolves to your local host IP address and can be used both within a Docker network and outside. On Kubernetes, we don't have a generic URL to let pods within a cluster access your local host. That means Edge service will interact with Keycloak via its service name, Polar Keycloak. When Spring Security redirects a user to Keycloak to log in, the browser will return an error because the Polar Keycloak URL cannot be resolved outside the cluster. To make that possible, we can update the local DNS configuration to resolve the Polar Keycloak hostname to the cluster IP address. Then a dedicated ingress will make it possible to access Keycloak when requests are directed to the Polar Keycloak hostname. If you're on Linux or Mac OS, you can map the Polar Keycloak hostname to the Minikube local IP address in the /etc/hosts file. On Linux, the IP address is the one returned by the Minikube IP profile polar command, as explained in Chapter 9. On Mac OS, it's going to be 127.0.0.1. Open a terminal window and run the following command. Make sure you replace the IP address placeholder with the cluster IP address depending on your operating system.
See this code?
On Windows, you must map the Polar Keycloak hostname to 127.0.0.1 in the hosts file. Open a PowerShell window as an administrator and run the following command.
See this code?
I have updated the scripts for deploying all the backing services for Polar Bookshop, including Keycloak and Polar UI. You can get them from the /chapter11/11end /polar-deployment/kubernetes/platform/development folder in the code repository accompanying the book, see this link, and copy them into the same path in your Polar deployment repository. The deployment also includes the configuration of a dedicated ingress for Keycloak, accepting requests directed to the Polar Keycloak hostname. At this point, you can run the /createcluster.sh script Polar deployment/kubernetes/platform/development to start a Minikube cluster and deploy all the backing services for Polar Bookshop. If you're on Linux, you'll be able to access Keycloak directly. If you're on Mac OS or Windows, remember to run the Minikube tunnel -- profile polar command first. Either way, you can open a browser window and access Keycloak at polar keycloak / include the final /. Finally, try running the entire system on Kubernetes after updating the deployment scripts for Edge service to configure the URLs for Polar UI and Keycloak. You can refer to the Chapter 11/11end folder in the code repository accompanying the book to check the final result. See this link. The next chapter will expand on the subject of security. It will cover how to propagate the authentication context from Edge service to the downstream applications and how to configure authorization.